in this session about applications of submodularity in machine learning.
Thank you, Peter, and thank you for the invitation. Great to be here. So, as Peter said, in the morning we talked about continuous optimization, and now we'll switch gears and talk a little bit about discrete optimization and set functions. And where do they occur in machine learning? So, to start, let me just sort of define to you what is a set function. So, in everything pretty much what I'll be talking about today, we will have a so-called ground set of items. So, for example, different items you could eat for lunch, and we will pick subsets of these items, and we will have a function that scores these subsets. So that's the set function, going from the power set to the reals. And this function could have many meanings. This function could be some kind of loss function. It could be a cost function of buying these things together. It could be a probability, a utility, or something like that. So we look at such functions. And just a little technicality, we'll just assume throughout that this function evaluates to 0 at the empty set, and we can compute it. So we're not going to talk about how we may compute it in applications you typically can. So, well, this looks nice and good and pretty easy. But what does this have to do with machine learning? So where do we have problems in machine learning and its application where such kinds of things actually come up? And essentially, it's almost everything to do with discrete optimization. So let's just go through some examples and see where this comes up. So first example is, let's say we want to decide where we want to make measurements, or essentially which kinds of variables we want to observe, which experiments we want to run, where we want to place sensors, etc. So that's essentially that out of the many positions where maybe I could take measurements, I have to take a small subset, and I want to maybe maximize something like an information. How much do I learn about the thing that I'm actually interested in? Another example are network optimization problems. So the example here says that I have a social network, and information can propagate through the network by people talking to each other, and it's actually a random process, so sort of a random diffusion process. So here what I'm picking is, out of all the nodes in my graph, I can pick a small subset, and what I want to maximize is the spread of the information if I start my process at this small subset of the nodes. And this example covers actually many different sub-examples with it. So this example is essentially data summarization. Say we have a large collection of images, and we want to show only a few of them to the user. So out of the ground set of all the images, I want a small subset that represents the data as well as possible. And the same thing we could do with summarization of documents and text. The same thing actually occurs when you try to do, say, matrix approximation and you sample a few columns of these matrices. It occurs in dictionary learning. You can actually also phrase object detection as this. So many, many examples what we want to do. And you can do this for large-scale learning or just for actually presenting things to a human. So all of these examples, I could maybe summarize as that there's some ground set, I want to pick some items, and I want to maximize something like a coverage or spread or diversity of the items that I'm picking, very roughly speaking. So I have some function that expresses that in some way, and I want to maximize this function.
Stefanie, sorry,
yes?
just what did you mean by representation in that?
Sort of like maybe the coverage of the content of this is very vague, obviously. So it may be the important directions of the data. It may be that there's minimize the redundancy, essentially. There may be many images in your collection that show basically the same thing, so it's enough to pick one of them. So web search, so like, this is pretty vague for now, so this is just to give you an intuition. Okay, sometimes maybe we may also want to do the opposite. So instead of maximizing coverage or spread, we may want to actually maximize the coherence of the items that we pick. So sort of do the opposite, and since we're doing the opposite, I'm sort of suggestively also already writing it as minimizing some function that does something like that. So what are examples of that? Well, one example is clustering and semi-supervised learning, where we want to pick out of all the data points that we have, we want to pick some that are somehow close together and sort of separated from the rest. So some kind of coherence or density. Same for semi-supervised learning. We want to maybe propagate the labels to the similar points. So the set of points that take the same label should be somehow similar. Very similar in flavor as this application. This actually comes from computer vision. We have an image. Now the ground set to pick from is all pixels in the image. And we want to pick a small subset of these that actually is an object. So obviously objects are somehow not random. They are somehow close together. So these pixels are probably close together spatially. And they may also look the same. And the last example here is that of, denoising or high-dimensional inference, where we are essentially trying to estimate a very high-dimensional signal that is actually sparse. So we know it's sparse, so essentially we are picking coordinates in that vector that are non-zero. Or similarly, we are maybe picking bases out of a large set of bases, the small few bases that actually represent that object. And sometimes there's more structure, and when there's structure, there's often also some kind of coherence of the coordinates that we're trying to pick. So all of these can be summarized somehow in this way. So far, so good. So basically what I've shown you is there's all these different problems at a very high level that can be phrased as maximizing or minimizing some kind of set function that's some kind of score or something like that. So far, that's not super useful because I can write many problems as optimizing a set function, and they can be very, very hard, and I can write them like that, so that doesn't help me so much. What we really need is we want to actually do computation with this, so we need some additional structure that makes this somehow efficiently doable. So what would that be? So if you think about continuous problems, there's essentially one thing that's very useful to have, and that's convexity. So let me just put a quote from a paper by Laszlo Lovász from 1983, where he compares some set of discrete functions with convex functions. So the first thing he says is, well, what is the thing why are convex functions so interesting? And he basically raises 4 points. The first one is they occur naturally in many, many applications. So they're actually useful because they're broadly applicable. The second thing is they are preserved under many different operations. So if I prove something about one convex function, most likely it generalizes. The third thing is that they are still sufficiently interesting, even though they are pretty broad, that there's some interesting mathematical theory that is associated with it. In particular, we can do efficient minimization of a convex function. So the question is, what would be sort of the discrete version of this? And to some extent, so as he goes on in this paper, he said it is less apparent, but we claim and hope to prove to a certain extent that this role is played by submodular set functions, and they share these 4 properties. So this is what my talk is going to be about, this set of submodular set functions, some of their properties, why they're interesting, and what we can do with them. Okay, so this is pretty much the outline for today. So we'll define submodularity. I'll give you some connections. Then we'll talk about mostly optimization. So there's many interesting topics, but optimization is the one for today. So we have submodular minimization in the first part, and in the second part we talk about submodular maximization and some more advanced topics, and that's going to be done by Andreas. Okay. So now, what is submodularity? What is a set function that is submodular? So submodularity is defined via so-called marginal gains, and essentially the marginal gain means if I already have a set of items that I picked and I add one more item, how much does my function value change? So that is the marginal gain of this value. In pictures, if you think about the sensor placement problem, I've already chosen 2 locations where I'm placing a sensor and I'm adding a third one. And then I just see how much does the information increase if I add this additional sensor. So now the specific property of submodular functions is that if I add more, if I already have chosen a larger set, then adding that single guy that I added in the first place gives me much less additional information. So you see, the more I know, the less I gain from adding that extra sensor here. So formally what this means that these marginal gains that I have, the larger the set is that I've already picked, the smaller is the gain. So they are diminishing gains, essentially. So that's the inequality. So A is a subset of B. And if I add S to A and I add S to B, then the gain that I get with a smaller set is always larger than the gain that I get with a bigger set. So that's a pretty intuitive inequality, I think. So this is one of the 2 inequalities that I want you to remember for today. So this is the diminishing returns property. And if my set function has this property, then it is a submodular function.
So you restrict your attention to monotone functions? That are monotone with respect to
no,
set?
so this actually, this inequality per se doesn't say it has to be monotone. So this could be negative. This could be even more negative. This could be positive. This could be negative. So this function, you're right, information is monotone, but in general, it doesn't need to be monotone. Any other questions so far?
Actually,
So if you take B as the full set, then it must be more than that.
If you take what as a full set?
B as the piece.
B, yes. So actually S should not be a member of B. So if you add S to a set where it's already in there, it's basically no change. So S is outside of A and B. Okay. So here we kind of view this as a utility function. You can view the same thing actually as a cost function. So what does it mean as a cost function? Here's just another picture example. It's the same inequality. What we get is diminishing costs. So essentially what we're modeling here is economies of scale. So if you think about it, you add maybe a drink to your meal. Once you have bought one drink, you maybe get a free refill of the same kind of drink. So the second drink basically comes for free. So that's the marginal cost. So that's why these functions are also important in economics. That's the intuition. So what we see also here is that actually this sort of diminishing gains can be sort of that for similar items we get these diminishing costs, but not necessarily for all possible items. So here if I would, instead of getting another soda, maybe I would get a coffee, that would maybe have the same kind of increase again. Okay, so here diminishing returns and diminishing costs. So this is the one inequality, and there's another equal definition of submodularity that goes not with A being a subset of B, but with two arbitrary sets, and that goes by union and intersection. So here's the inequality. So we take two arbitrary sets, S and T, and we evaluate that function at these two sets at their union and their intersection. And what should hold is that f of s plus f of t is always bigger or equal than function evaluated at the union and plus function evaluated at the intersection. So these two are equal. It's actually becomes more obvious if you match up the terms correctly, that one sort of implies the other. If you make B the T and A union E the S, then A is the intersection and B union E, the largest guy, is the S union T. So you can sort of by rearrangement prove that these are actually equivalent here. And this is the second definition. If you want to show submodularity, one is as good as the other. The upper one is often more intuitive. Sometimes the lower one is easier to show. So these are the two definitions. If your function satisfies this, it's a submodular function. So we have the abstract definition. Let's look at now some examples of where does this submodularity property actually come up, a bit more formally. The first function is essentially the set function analog of a linear function. So we have our ground set, and each item in my ground set has a weight. And the function evaluated at a subset is just take the sum of the weights of these elements in the set. Pretty simple. It's just linear. So, and this is also called a modular function. So this function is submodular and supermodular. It's linear. So supermodular is sort of the negative submodularity, like convexity and concavity. So what is the marginal gain for this function? Well, it's actually pretty simple. If I see how much does my function increase, if I add a single element E to my set, it's basically the weight of that element is the increase. And that is in fact independent of A. That holds for all possible sets that I might be adding this to. So hence the marginal gains are always the same, whatever the sets are. So we get the inequality actually holding with equality. So this function is submodular. Okay, so that is pretty much the simplest function I could have as a submodular function. Let's try to go a little bit more sophisticated. Just a little bit. My second example is a coverage function. So what is coverage here? My ground set is maybe the set of all locations where I could place a sensor, and here I'm modeling a sensor simply as a disk that is the sort of area covered by this sensor. And now my function just takes the union of all these disks that I covered. So the marginal gain is here sort of indicated by the green color, the additional area that I gain from adding this additional sensor. And now the more blue sensors I've already placed, the smaller is the marginal gain that I have. So it can only decrease, it can never increase. So that is proof by picture that the coverage function is a submodular function. And this coverage function has many different applications. In fact, the other example I talked about in the beginning, the network, diffusion in networks or spread in networks, is actually just essentially a stochastic version of coverage, and hence this is also a submodular function, the expected coverage. Okay. Let's now look at a few other examples. So this sensing problem that I talked about, that was sort of our running example, we could also model this in a bit more sophisticated way than just doing disks that we cover fully. So maybe there's something more about sort of a probabilistic model or information that we can bring in. So here, the way I could model this, for example, is that I have a random variable for the unknown temperature in each of the locations. And of course, temperatures in adjacent locations are not completely independent, so we are drawing here these edges in the graphical model. So now what I can observe actually is I want to learn about the temperature everywhere to sort of detect maybe there's a fire outbreak. What I can observe is actually the true underlying temperature plus some noise. So these are sort of my possible observed variables x. So now the task is I select some of these x variables to learn as much of the y as possible. So what would be a good objective function for this thing? It's maybe how much do I reduce my uncertainty about the y's given that I select some of the x's. So the way we could write this is by using entropy, the reduction in entropy. So I have the entropy of the y variables before I do any measurements, and the entropy conditions on that I have actually taken measurements in the locations in A. So these are the random variables indexed by A. And this is nothing else than the mutual information between the hidden variables y and my observed variables xi. And that too is a submodular function. It's a submodular function if the x variables are conditionally independent given the y's. So I'm not going to show you the full proof of that, but the proof essentially relies on the fact that entropy is a submodular function. And let me just show you the proof for that one. So let's look at the entropy function per se. So for entropy, we have a set of discrete random variables, and that's basically our ground set to choose from. And now the function that we're looking at is the joint entropy of picking that subset of variables. So let's look at the marginal gain for this entropy. Essentially, it's the entropy of the larger set minus the entropy of the A by itself. So this particular difference has a name and is essentially the conditional entropy of the variable xi given all the other variables xi. So it's just the conditional entropy. So now what happens? If I condition on a larger set, my entropy of this E can only decrease. Knowing more never increases my uncertainty, it actually only decreases it. So the more information never hurts. That means the entropy only shrinks if I condition on more variables here. And that gives me the diminishing marginal returns, and that shows that entropy is actually a submodular function. Okay. So the entropy example also points to one more thing, actually. So if you remember, entropy has this very specific property that if I take variables that are statistically independent, the entropy is actually additive. And if there's some dependence between the variables, the entropy is going to be sub-additive. So I'll have actually this submodularity inequality satisfied with strict inequality, otherwise just equality. So in a similar sense, so essentially what my submodularity actually does here, it sort of gives me some measure of dependence. It's more submodular if it's more dependent, essentially. So this kind of independence or dependence measure actually is satisfied by many other submodular functions. So here's another type of dependence that is modeled by a submodular function, and that is dependence of vectors, linear dependence. So think about that your ground set of elements is just a set of vectors, and you're picking a subset of these vectors, putting them together in a matrix, and looking at the rank of this matrix. So essentially, this is the number of vectors if they are linearly independent, and otherwise it's smaller than the number. So this rank function is also a submodular function, and again, it is additive, so it's actually a modular function if there's full independence between the items, and otherwise it's strictly submodular, strictly smaller. And these two actually are just two examples. There's many other combinatorial notions of rank that are satisfied by submodular functions or expressed by submodular functions. Okay, so far what we looked at was submodular functions that sort of, as my set grows, the function value can only increase. So these are monotone functions. Let's look at one more example that's also a pretty well-known one that is not a monotone function, that actually can also, function value can go down as your set grows. So say we are given a graph and we're picking a subset of the nodes in this graph and looking at the cut around these nodes. So we're essentially counting the number of edges that connect our set with the rest of the graph. So that's the graph cut function. This could also be a weighted sum if the graph is weighted. So basically minimum cut problem is trying to find the set that minimizes this cut. So let's look at, is the cut function a submodular function? And to prove this, let's just look at the cut function on 2 nodes and 1 edge. That's the simplest we can do. And this time we will not look at the diminishing returns, but we will look at the union intersection thing. So if you remember, you want f of s plus f of t to be bigger than the union and the intersection. So here we have a ground set of 2 items. So the really only interesting part is letting s be u and t be v. So you can check that for yourself. That's the only thing that's really slightly non-trivial. So we need this black inequality to hold. So let's just check it. F evaluated at u is basically, we pick u, so we have to cut the edge. V is not in our set. So we get essentially the weight of that edge as the function value. Similarly, if we pick v, the other side, we also have to cut the edge. We get the function value. Now, if we pick both of them, we are not cutting any edge. There's no edge anymore. So we get 0, and the empty set is also going to be 0. Hence, what this inequality shows is that 2 times the edge weight is bigger than 0. And if the edge weights are non-negative, this function is going to be submodular. So now our big graph is, of course, a bit larger. But if you think about the big graph, is actually just a sum of functions like this. And the sum of submodular functions is also a submodular function. So hence, I have proved that the graph cut is a submodular function. So minimum cut problem is actually a very specific case of a submodular minimization problem. Okay, so we've seen a few examples now from information theory to coverage to graph cuts. Submodular functions can also come up in a few other settings, and that is in a more generalized sense in probability distributions. So we can have distributions that are log submodular or log supermodular, which means that the distribution is essentially defined by a submodular function that you exponentiate. Or you satisfy this inequality with a product instead of a sum. So there's 2 ways this could go. It could be log supermodular, or like basically minus f up there or plus f there. So what are the distributions that satisfy this? What are the properties that they have? If you think about a submodular, so this is a minus f. So basically the distribution has high probability if the submodular function is small. So basically this is like submodular minimization. This is like we are trying to encourage coherence and smoothness and so on. So these distributions are essentially associated with positive correlation. So in fact, they imply what is called positive association. So they are also called totally positive distributions. And let's just look at an example. Example is the ferromagnetic Ising model, or conditional random fields with submodular potentials. On applications, this is, again, computer vision and image segmentation. So let's say we actually have a Markov random field, a probabilistic model, over this image where each of these variables corresponds to a pixel. So now this is actually strictly, it doesn't look like a subset selection problem. I said, well, we are sort of selecting a subset of the pixels. That's the same as assigning variables 0, 1 values to my variables. Because essentially I can write every set as a binary indicator vector. So I have my ground set B here, and I take a subset S. That is the same as taking an indicator vector which is the. So I'm just writing this down here because we'll need this all over again. And essentially, whenever I speak about vectors, they will have the same dimensionality as my ground set, and there will be 1 coordinate for each element in my set, in my ground set. And I'll have 1s for the guys that I'm actually selecting. So now this is the same as a distribution over binary random variables. So now let's look at this particular example again. So what we want is actually a distribution that tells me how likely is it that this set of 1s is actually an object. So it's more likely to be an object if you're somehow close, basically an object corresponds to pixels that are close to each other rather than pixels that are all over the place. So we want actually positive correlations between the ones and the pixels that we're choosing. So hence this is typically modeled by these kinds of attractive potentials. So being close together is the same as sort of being more likely. This function, in fact, is the same as our graph cut function, just raised to the e. So the way you could see this is that, well, what we have is we have basically pairwise potential. So basically for two variables, we say that it's more likely that they take the same label than different labels. So we get a penalty whenever there's a difference. Now, if we look at the ones that we actually pick as the ones that's sort of the object, we get a penalty wherever we cross. And that's basically the graph cut. So that's also well known. So this is a log submodular function, log supermodular because we have the minus f. So what is the gain of knowing that this is a log submodular distribution rather than something else? Well, essentially it gives you some computational benefits. So first, finding the mode is like minimizing the submodular function, and you also get approximation algorithms for computing the partition function and the marginals and so on, and Andreas will talk a little bit about that. Okay, so this was log supermodular distribution. So we can also have the opposite, which is log submodular distribution. So again, while the first one sort of prefers sets that are somehow together and sort of induce positive correlations, these are more associated with negative correlations. And a particular example of these are the so-called determinantal point processes that have been also similar to volume sampling. So the way this works is as follows. Let's say I have some data points. Each data point is represented as a feature vector, let's say these two images, and the probability of these two occurring together is proportional to the volume that is spanned by these feature vectors. In fact, the square of the volume. So if they are more similar, their feature vectors point sort of more in the same direction. The angle is smaller, so the volume that's spanned by them is smaller. And this doesn't work only for two, it also generalizes to higher dimensions. So that's the distribution, and you see already the distribution sort of prefers vectors that are more orthogonal to each other. And if the vectors are linearly dependent, this is going to be actually 0. So this can be conveniently represented as the determinant of submatrices of a large inner product matrix, which is called L here. So basically this matrix is indexed by the variables in my ground set, picking subsets of these variables, and that gives me a submatrix. I'll get the determinant. So that thing is log submodular. So these distributions are also interesting. They're sort of the relation between positive correlation and log supermodularity is a bit stronger than the relation between negative correlations and log submodular distributions, but essentially a subset of these have very strong negative correlations, and that induces, for example, that you can get fast sampling algorithms. So there's many computational benefits that we get here. Okay, so what we see is submodular functions come up in many places. What we'll see also throughout the tutorial is that we'll get many nice computational properties out of these. In fact, submodular functions here sort of an overview of where all they come up and where sort of historically they have arisen. And there's many different areas here. That's graph theory, there's information theory, game theory, stochastic processes, and also machine learning. And what you see on the outside is sort of some of the people who were the first to study really submodular functions and define them. So the first one was maybe Choquet in 1955 in his theory of capacities, and then in about the same time, 1971, Shapley and Edmonds studied submodular polyhedra that we'll talk about, and Lovaas then studied the Lovaas extension. Just a little overview. So now let's go back a little bit to the properties of the submodular functions. So we saw lots of examples. And in the beginning I said, well, there's some analogy between submodularity and convexity. And the question is, does it actually hold any water? Are submodular functions really like convex functions, or are they maybe really like concave functions? So what are they really? And in fact, the truth is a little bit of both. So on the one hand, they are like convex functions because, as we will see, you can actually take a submodular function, you can make it into a convex function, and you can optimize that instead. And there's actually also associated duality theory, and in all of these inequalities, submodular functions sort of behave like convex functions. They always show up on that side of the inequality, essentially. So there are strong relations and analogies to convex functions. But on the other hand, if you think about the diminishing returns property per se, so diminishing returns is like I take a set and I add something to it and I see how much does my value increase. That's like a discrete derivative. So diminishing returns is actually more like shrinking derivatives. And typically I have shrinking derivatives if I have a concave function. So in that sense, it's actually more like concavity. Now, the analogy to concavity goes a little bit further than this sort of intuition that I have that my diminishing returns are actually like concavity. I could define a set function as follows, that I take the cardinality of the set, that's already a set function, and I take some kind of function, scalar function g, applied to the cardinality. That's a set function. It basically just, I could put any kind of scalar function there. So when is this a submodular function? And it turns out this is a submodular function if and only if this g function here is actually a concave function. So intuitively, you can think about it then that, well, if this was sort of the cardinality, this is what the function would behave like. And this is the only thing that would give you these diminishing returns. So in that sense, it's also very related to concavity. Now I can take this a bit further, and instead of taking the cardinality here, I could have something that's like g of a sum of weights, where the weights are non-negative. So likewise, this g should be a concave function. So there's actually a variety of functions I can define that way. And this thing now I can take slightly further in the following sense, that I can take these functions and stack them up. So now I'm already sort of putting it suggestively. So here I have sort of one function that sums up the weights of the elements in my set, which is the same as taking an inner product with this indicator vector. And I can do this with one function. I can do this actually with a bunch of different functions, each with a different g, and with a different weight function here. And now whatever comes out of these values, I can take them and I can do essentially the same operation again, over and over again. So what I get is actually something that looks like a deep net. A very, very special one, but I can get what are called deep submodular functions. And it turns out if I take now the values at these upper nodes here and I sum them up, this is a submodular function. I can go as deep as I want. But for that, these functions g should be monotone and concave.
Question, the
Yes?
weights are non-negative?
Yes. Yeah, so it has to be non-negative. So this is a submodular function. So that's the relation to concavity. Now the relation to convexity and concavity actually gets a little bit more pronounced even when we look at other generalizations of submodular functions. So far I said, well, submodular function is actually always a set function, and it's not completely true. So a submodular function actually can be defined more broadly in what are called distributive lattices. Think about integer vectors. And now we have essentially the union operation becomes and the intersection operations become the join and the meet, which means we take element-wise maximum and element-wise minimum of my vectors, coordinate-wise. So if my function now satisfies this inequality, which is basically the same as the union and intersection inequality that we saw, then this is a submodular function. So in this setting, actually, diminishing returns and submodularity are not strictly the same anymore. Diminishing returns is stronger than submodularity. Yes?
Maybe from the previous slide, I just realized, so the weights are fixed. They're not going to be learned.
Oh, you can learn them.
And that's going to be polynomial time?
Probably not. I'm not sure.
Okay,
yeah, so I don't know. So we can talk about
the deep nets is not quite that you can learn the weights in polynomial time.
Oh, you can learn the weights, and in fact, it's essentially, I don't want to say anything wrong right now about the polynomial time learning.
That would be surprising, yeah.
Yeah, so I'm not exactly sure you can do it, but I also don't have a proof immediately that you cannot.
So, I see. So you just have weights and somehow you define this network.
Yeah, so I didn't actually say where do these weights come from, where do the functions come from. You can learn them from data, for sure. You can do you can like approximately learn them,
yeah.
right? Maybe you can efficiently like fully learn them. Would be interesting.
When you say the function is submodular, it's submodular in X.
It's a modular in X, yes, not in W. Right.
So it's not clear how you've done it, yeah.
Yeah. So it's not an optimization over the W here that will be submodular, it's the X function, right? Okay, so let's go back to these. What kinds of functions are these? And it turns out this class of functions, it contains convex functions and it contains concave functions, and it contains functions that are neither, like this one, for example. So this function class is sort of different. The nice thing is that many of the optimization algorithms and results that we'll talk about today, they kind of generalize to that setting as well. The function class is a bit different. Okay, so with that, let me just wrap up the first part of, the first half of this part. So we saw submodular set functions, which are sort of the core, which have two different properties. Essentially, relations to convexity will be used for minimization and maximizing coherence in modeling. Diminishing returns will be used for maximization. They're sort of like concavity and for maximizing diversity. Then we saw a few different relations to non-convex optimization if you optimize these functions in the previous slide. In fact, Andreas will also talk a little bit about non-convex relaxations for submodular optimization. We'll have relations to probability measures. That actually is an entire research area by itself. And then we have many different examples of submodular functions. So now let's look a little bit actually about the computational properties of these functions and about optimization. And the first part will be minimizing a submodular function. So we have our function. We want to find the minimum value. So now that is a discrete optimization problem. How do we use the properties of submodularity to make this a ideally polynomial time thing to do? And the idea that we'll follow here throughout is, well, we'll use a relaxation. So we'll take our set function, and in fact, we'll view it as a function defined over binary vectors, which looks like this. So it's defined only some parts of the space. And we will take this function and relax it to an optimization problem over the hypercube, continuous functions. So we know how to do continuous optimization after this morning, so that's what we'll try to use. The question is, how are we going to do that? So what would be the function that sits here that sort of interpolates this thing we get from our subsets? And well, one natural thing to do is, we have this function, we can evaluate it only on subsets or only on binary vectors, but well, we can make it an expectation. So if we had a distribution over sets that's somehow defined by the vector x, then we can make it a function that's defined over continuous vectors x. That's what we're going to do. The question is only how to do this in a way that this function f has some nice properties that we can use. And the idea in the end is pretty simple. We'll just do threshold rounding. So here's the idea. So here's our example vector. We have our vector x, and we'll assume for the moment it's between 0 and 1. And we'll uniformly pick a threshold, theta, between 0 and 1. And now remember, each of the coordinates of this vector, as I said, corresponds to one element in my ground set. And now I just take this as an indicator vector. So I threshold this vector, and I pick all the elements that have coordinates above the threshold. So here's the illustration. I take my theta, and I pick the first 3, and I discard the others. So you see that with this particular sampling strategy, effectively for this vector, I can only sample 3 different sets. I can sample this one guy, I can sample the first 3, or everything together. There's no way I can, for example, pick the last one and the first one or something like that. So it's very specific, but it's very simple. And now I define my function to be the expectation of this. So I take this subset, I evaluate the function on this. So this can in fact be done for any set function, and it's pretty easy to compute. So just to show you that this actually already gives some interesting functions, let me give you two examples. Let's say we have our special example vector, which is 0.8 and 0.5. It could be really anything. So which means our ground set has two items. We have two coordinates, so we have item A and item B. So now if I do this threshold rounding, the probability of getting both of them is 0.5. So the probability of getting A and B is 0.5. The probability of getting just B is the difference between these. This is 0.3. And with probability 0.2, I'm going to get the empty set, and that's it. So that's my sampling. So now what is my extension here? And this is the Lovász extension. It's going to be 0.5 times the function evaluated at both guys. Plus 0.3 function evaluated just at B. Plus 0.2 evaluated at the empty set, which we set is 0. So now let's look at some examples. Let me give you the first example function. Let's say f of s is minimum of the cardinality and 1. So this is, in fact, it looks like a very boring function. This function is 1 everywhere except for the empty set. So let's do this exercise. So what is f of x? F of x is 0.5 times 1, because that's not the empty set, plus 0.3 times 1, which is 0.8. Okay, so if you look at this and go through it a bit more and think about it a bit more, what this actually is, this always gives you the maximum coordinate of x. So this, in fact, since these vectors are all non-negative, this is going to be the L infinity norm of the vector that I get out as the specific Lovász extension. So this is actually the second example. Let's take the graph cut, where again we take a graph on two nodes, A and B. So basically that means if I take either A or either B, I'm going to have, say, value 1, and otherwise I'm going to have value 0. I'm going to cut this. So again, what is this going to be? This is going to be 0.5 times 0 plus 0.3 times 1, which is going to be 0.3. And more generally, what this is going to be xa minus xb. So again, coordinates correspond to the ground set elements. This function is also called the total variation. So if you do this for a larger graph, what comes out is what is called the total variation function that you get as the Lovász extension of the graph cut function. Okay, so that's our Lovász extension. Any questions so far? Yeah.
Can you explain the notation expectation with the subscript?
Oh, okay, this is a bit low. So basically what this means is expectation that over the randomness in theta. So you pick theta between 0, 1, and then you sample the s theta as taking all the elements that have x values above theta. Yeah. So that's just the expectation with respect to these s theta sets. That, yeah, just think about it. And there's many other ways you could sample sets by a distribution defined by x. And that's just one of them, and that's the one we are going to use. But it turns out this one has particularly nice properties. So here's a picture of this extension. So this is again in 2D. We have just two elements. Here's our set function. And now we plot the Lovász extension. The Lovász extension looks like this piecewise linear convex function here. So that actually is nice, because if it was always convex, we could use convex optimization to minimize it. And in fact, that's the case. That's a theorem. You can define this Lovász extension for any kind of set function, but if the set function is submodular, in fact, if and only if, then this Lovász extension is going to be a convex function. So how do you see this? Let me just give you one argument in one direction. And that is that if the function is submodular, you can also write this Lovász extension as the pointwise maximum of a set of linear functions. And the pointwise maximum of a set of linear functions, that's like, think of some lines, and sort of the maximum over that, it's always going to be a convex function. So this function that looks like this, a maximum over linear function, is always going to be convex. And hence, this is always a convex function. So now in this kind of definition, there's this thing showing up. So I said it's a maximum of linear functions, but of what kind of linear functions? So these linear functions are defined by a polytope, and that polytope is essentially what makes all of submodular minimization tractable. So this is the so-called base polytope. Okay, so, and remember, this is our relaxation, so we will eventually want to minimize f of x. So what is the base polytope? To understand the base polytope, we'll first define the submodular polyhedron, which is sort of a superset of this thing. So this is the definition. It looks at all vectors, and it has an exponential number of inequalities, one inequality for each subset of my ground set. So what the inequality essentially says is that this vector, I sum up all the elements that are in A, and this should be upper bounded by f of A. So essentially, it's a set of linear functions that are upper bounded by my submodular function. And now the base polytope is a particular phase thereof where the last inequality is tight. So this vector should actually sum up to f evaluated at the ground set. That's the base polytope, and this is what it looks like. So far so good. It's some polytope that's defined by my submodular function. And in fact, again, just like here, there's actually base polytopes. Even if you have never heard about a base polytope, there are some examples that you probably have heard of. So one is the probability simplex, for example, which is the base polytope of this function here. The second thing is the spanning tree polytope, which is essentially the convex hull of all indicator vectors of spanning trees in a graph. And the last one, it's called the example here is the permutahedron. So that thing, essentially, think of a vector 1, 2 to n, and think of all possible permutations of these numbers. And now you have a set of vectors, and now take the convex hull of these vectors. So each vertex of that polytope is a permutation of 1 to n. That's called the permutahedron. That's a base polytope of a submodular function. Okay, so why is this polytope interesting? Also, okay, here's what it looks like in 3D, just for the picture. So why is this thing interesting, or sort of what's good about it? Essentially, what I have is I have this polytope that I defined for you. It's defined by exponentially many constraints, and now I have my function, which is actually a linear optimization over these lots and lots of constraints. So that's per se not super good, because it's too large a program to write it even like tractably down. Can we even compute this? So of course I already defined to you something that we can, but could we even solve this thing here? And it turns out that the structure of these polytopes is so nice that essentially the simplest possible algorithm works to do this linear optimization. And this is Edmond's greedy algorithm. So let me just give you the intuition. Think about this inner product up there. It's really like yi times xi, and we sum up over this. So essentially, wherever x is large, y should be large ideally. So the way we do this is we sort x, the coordinates of x, and we look at the first coordinate, that's the largest one. And then we make y as large as possible on that coordinate until we hit the constraint. And then we fix that, and we look at the second coordinate, we make y as large as possible on that one, and so on and so forth. That's why it's called greedy. And if you do this, essentially what this corresponds to is defining these sets of elements, because all of these are ground set elements, and you get your optimal solution essentially as a vector of marginal gains. So just as a vector of differences of my function. This is closed form. So essentially I can do this optimization even though it looks complex in n log n time. So that's a very amazing result that you can actually do this, and it very much relates to the structure of these polytopes. So that's, for once, it's interesting because it actually makes this Lovász extension, if we had defined it that way, tractable. The second thing is that it actually allows us or enables us to do optimization with this Lovász extension. If you think about this expectation formulation, it's not really easy to do any kind of optimization with it. this thing is a convex function, I can do optimization if I could compute something like a gradient for this function. So this essentially defines a so-called subgradient of the function. And that means we can do optimization. So we heard a lot about gradient descent. Essentially, this function looks like piecewise linear, so I'll just draw for you what is a subgradient. So if you think about a convex function, a gradient is essentially something that touches it. Okay, this is a very bad picture. Okay, so here we have the gradient that touches the function is sort of the tightest lower bound to the function at this point. If I have a function that is this piecewise linear function, it's not differential at these corner points. But what I'll have is I'll have a number of different linear functions that are sort of lower bounds to the functions and touch it at this point. So all of these parts, guys, are the subgradients. So now if I want to minimize this function, the simplest thing I can do is gradient descent. I take a point, I go a little bit in the direction of the negative gradient, and I do this over and over again. So for these functions, I don't have a gradient, but I can essentially do the same thing, and I can use subgradients instead. I need to be a bit more careful in the step sizes, but essentially it works. So that means if I can compute subgradients, I can actually optimize the function. So this is actually very important, and the subgradient is exactly this vector that I get out here. Okay. So now we know the function, we can do optimization over it.
Can you explain why this is the subgradient?
This thing? Okay, so basically if you think about a maximum of linear functions, so let's say we have this, and now the gradient at a point here is pretty obvious, right? It's this function here. A gradient at this point is going to be this function, so essentially the gradient is always the function of these linear functions that is the current maximizer, the argmax. So basically that's all it is. And if I'm at this point, both of these or any convex combinations of these is going to be a subgradient. So basically all I need is the argmax of this thing. But the argmax of this thing is exactly the thing that maximizes the y that maximizes this. That's why it's going to be the subgradient. That's the one we compute. Okay, so let's go back to our big picture. So we have this Lovász extension now, which is defined via these polytopes. So what we did was we took our discrete optimization problem, we derived this Lovász extension, and we said, well, we'll do this relaxation, and we'll solve this convex optimization problem instead. And we can actually do this because we can compute subgradients, and there's better methods than subgradient descent to do it potentially, but this is essentially the framework. And the tractability of this hinged on these polytopes. So now the only thing that we need to know is, okay, now we have this. How do we go back to the discrete solution? So now we have minimized this thing. We have to go back to the discrete solution originally. This may have a fractional solution. And this is, in fact, it's not super hard to prove that this relaxation is actually exact. So if I minimize this, I'm going to get exactly the same value as if I would minimize the set function directly. And the rounding is actually exceptionally easy. So if you think about it, this is actually an expectation over these s theta functions. And one of these is going to be the minimizer. And in fact, if you want to even easier, you can just take all the coordinates that have larger than 0 entries. And these two results together essentially, plus the ellipsoid algorithm when it came up, showed that submodular minimization can actually be done in polynomial time. Not yet very practical polynomial time, but polynomial time. So that was a big achievement. Now, of course, if we look at this framework, there's actually many different optimization algorithms we could apply to this and get out different submodular minimization algorithms. And all of these lead to a different algorithm. So here's just an overview of some of these. And essentially, all of them solve essentially the same problem. All of them minimize this Lovász extension in different ways. There's essentially two different directions that people have gone here. So the first one was just applying the ellipsoid method. You can do subgradients, you can do cutting planes, many other things. Another approach is to do combinatorial. So that the motivation was basically, well, minimum cut problem is one example of a submodular minimization problem. We can have nice polynomial time combinatorial algorithms to solve this. can we have a combinatorial algorithm to solve that problem? And essentially you can. I'm not going to show it here, I don't have the time. Essentially it solves the dual of this low-pass extension minimization and uses network flow algorithms to stay in the polytope essentially.
What are these parameters T and M?
Okay, so M is the maximum value that the function can take. T is the time to evaluate the function. Is this oracle evaluation of the function. So in addition to these algorithms, there's actually a slightly different route you can do also via convex optimization by using a slightly different relaxation of the problem. And this leads us to the so-called minimum norm point or Fujishige-Wolf algorithm. So the way this goes is, if you remember, before that we were just minimizing the low-pass extension over the hypercube. You can do away with the hypercube constraint and instead put some separable, strongly convex function up here. Essentially think of the squared norm. So now we solve this problem. This problem has this basically strong convexity property. It grows faster than the low-pass extension. It's still non-smooth.
F is the low-pass extension?
Yes, F is the low-pass extension. So why would we want to solve this? Obviously, it has a very different solution from minimizing the low-pass extension per se, because we have this very strong perturbation here. And there's no epsilon involved, we don't need it. So the reason is that this problem actually solves a complete parametric series of problems. So if you look at this set of problems, we have minimized the set function plus some penalty on the cardinality. And it essentially, if I solve this one, I can read out the solutions for this for all possible alpha, in particular alpha equals 1. And the way this works is actually pretty amazing. So I take the optimal solution, the x star from the left-hand side, and I threshold it at alpha, and that's going to give me the optimal solution for the right-hand side problem. And why this works, it relies on submodularity, but it's pretty amazing. And now this problem over there, it has also some nice optimization properties. In particular that it grows pretty fast. I can take the dual of this problem. Essentially, the upper and lower things are the same. If I can solve one, I can solve the other. I can translate the solutions. So the problem that people often solve is this one. It's an optimization problem now over the base polytope, but instead of linear, it has this quadratic thing. It's basically finding the point in the base polytope that is closest to 0, that has the smallest. So that thing, the squared norm looks like a pretty easy thing to optimize, but now we have this constraint. And I told you this is like this polytope with the exponentially many constraints. How would we solve that? And so now we can do possibly something like projected gradient descent, but as Elad pointed to, sort of actually computing whether we are inside or outside of this polytope is pretty non-trivial. Essentially, that's the entire problem we want to solve. So essentially, you need to solve a submodular minimization problem to determine that. That's not what we want to do. So instead, what we'll do is we rely on the fact that we can do efficient linear optimization over this polytope. And we'll use these Frank-Wolf methods. So Frank-Wolf algorithm is basically, I think, one of the oldest nonlinear optimization techniques at a time when people were just thinking about linear optimization. So it's just a reduction, essentially, to iterative linear optimization. Since I'm not sure if you have seen it before, let me just illustrate roughly the idea of it. So we want to optimize over this polytope. This would be the unconstrained solution. So the colors indicate sort of function values here. We start at some arbitrary point. Now, if you want to do gradient descent, we would just go into the direction of the negative gradient. But again, this is a problem because if we were here, we sort of don't know if we're going out of the polytope or not. We don't want that. So instead, what we do is we do a linear optimization over this thing and find the corner point of this that is most aligned with a negative gradient. And now we know if we go somewhere between here, we take a convex combination of these points, anywhere between the line, we're going to be inside of the polytope. So we take some point inside of that. And we are going sort of into a good direction, we know, because this is aligned with a gradient. So we'll find a point along this line, and that's our next point. And then we repeat. We compute the gradient, negative gradient. We find a point by linear optimization over the polytope, which is the n log n sorting thing that I talked about. And you again go somewhere between here and here. You know you're never going to go outside the polytope. And so on. And you will converge to the optimum. So this is the idea of the Frank-Wolf algorithm. You can do slightly faster than that by doing some sort of more fancy things with having active sets of vertices, etc. But this is sort of the main idea. Always only do linear optimization. We know how to do that.
Question?
Yes.
So, could we go back one more slide? Yeah. One more. Sorry. So this was for what problem? I
This
think
is
on the
for
previous slide-
minimizing the norm over the base polytope.
But you were connecting it to the. Can we go to the previous slide?
Oh, okay. So what it does is this
Yeah.
one. So essentially, this problem is the dual of this problem. So if we solve this problem, essentially you flip the sign. You take the y star of this, you make it minus y star. That's going to be the optimal solution for this one. And if you have the optimal solution for this one, you know how to threshold it to get the optimal solutions here. So you threshold it at 0 essentially. You take, for this guy, you take all the coordinates that are negative, or you flip the sign and take all coordinates that are positive, and that solves your problem.
I see. So the Frank-Wolf is a faster way to do that? Is that what?
Oh, Frank-Wolf is just one way to do this. It is essentially, if you do the one I showed you, it's not super fast. It converges as 1 over t. And if you translate this convergence to the discrete problem, it's going to be 1 over root t. But it's an algorithm. And you can, so here's the empirical result. So you can speed this up empirically by doing something, basically active set type methods that I'm not going to talk about. But here's the empirical convergence result. So this is basically number of iterations for different convex optimization methods. And here's the minimum norm point algorithm, the faster version of it. So it converges much faster than the other ones.
So what's the requirement from the function for the Frank-Wolf to converge? I mean, here it was the quadratic function. But
Yeah.
does it work for any function? What are the
It works for any smooth convex function. Differentiable, yeah, convex. The convergence speed depends then a bit on the actual polytope and the function properties, but that's essentially it. And linear optimization over the polytope is possible. That's another. Okay. So let me just give you a quick summary here. So we saw that submodularity has very close connections to convexity. It's very good for optimization. We get these duality results. It actually has many implications for machine learning too. So for example, what you can do is you can take your submodular functions and you can actually get norms for it for sparse inference, structured sparsity essentially. You can get faster decomposition in parallel algorithms by using this sort of smooth, not smooth, but strongly convex second relaxation that I talked about. And you can also do variational inference for log submodular distributions. In the interest of time, so I had this example of how to actually do structured sparsity via the Loas extension. I'm going to skip this. Main idea is coordinate selection sparsity is like a subset selection problem. You can relax that by putting a submodular function. Using the Loas extension is essentially like going from L0 to L1. You can get structured norms out of the Loas extension. So with that, let me just wrap up. We saw submodular minimization you can do via convex optimization. There's a few other things you can do for special cases, such as minimum cut, for example, and reducing functions to a cut problem. So that is another interesting problem, which functions you can actually reduce to that. So-called decomposable functions that are sums of simpler submodular functions, and also symmetric functions where the function is the same as the complement. In the second half of the tutorial, Andreas will talk a little bit more about the relations to concavity and diminishing returns and what you can do with that. Submodular maximization is. So I think now it's time for the break, and thanks all for your attention.
All right, so to get us back on track, we probably should get questions offline and